guys! Welcome to our exhibit on liquid nitrogen and space shuttle tiles. Thank you so much for joining us, and we really hope you enjoy the presentation. The temperature in space can get to both extremes, super cold and super hot. Let's talk about the cold portion of space. Space can get to negative 454 degrees Fahrenheit. For those of you who know what absolute zero is, that's about 3 Kelvin, which is super close to absolute zero. For those of you who don't know, absolute zero is so cold that everything stops moving. It's called absolute zero because it's 0 Kelvin, and Kelvin is just another temperature system like Fahrenheit or Celsius. That's super cold though. In order to model that on Earth without actually letting the temperature get that cold, we use something called liquid nitrogen. Let's watch a demo where we see a balloon submerged in liquid nitrogen.
We try to model that using something that's in here. Does anyone know what this is? Correct! Yes, it is liquid nitrogen. So we can model our space applications using liquid nitrogen. So let's kind of experiment though with that. Liquid nitrogen is really cold. That's why we're using gloves. And I should wear those too. So Brandon's actually going to model this right now. He's going to submerge a balloon in liquid nitrogen. But can someone tell me what's going to happen if he were to submerge it? It's going to deflate? Okay. What do you guys think? Yes? It's going to freeze? Okay. So let's try it out.
Where are your dogs?
So if you can hear that, that's not paper, that's still a balloon. But you can see it actually deflates. Really cool, right? But it actually increases in volume really quickly.
You can see the balloon got a lot smaller. We can model that using something called the ideal gas law, which is the equation that's on the slide. We know that when we stuck the balloon in liquid nitrogen, the temperature went down. The P, N, and the R in the equation stay the same, which means that in response to the decrease in temperature, volume has to also go down. The air inside the balloon is not exactly an ideal gas, but it works basically the same way. This, however, is not how it works with solids. We'll take a look at how it works with pennies, but it's important to know which pennies we use. Pennies from before 1982, like the one that's on the left of the slide, were made from just copper, whereas pennies after 1982, on the right of the slide, are made from a copper and zinc blend. Now on to the demo.
Right now we're going to dump a penny, actually a few pennies, into liquid nitrogen. So, the question is, what do you think is going to happen if I were to take I would submerge the penny and hit it with a hammer? Do you think it's going to break? Yes. If I were to break it with a hammer, do you think it's going to break in one piece or multiple pieces? Multiple pieces? Is that because I'm strong or is it because because of the penny? Because of the penny? Okay, let's try it out. Hopefully everyone can see it. This penny is 1970. In fact, you can actually see the difference in the material. Okay, so you can actually see the difference. This is a lot brighter than this one. That's just because of the combination. So let's try smashing it. So I actually broke into a few pieces.
We can explain what just happened by talking about something called structural integrity. In fancy terms, cold temperatures reduce the structural integrity of a material. When we stuck the penny in liquid nitrogen, it did just that. To put it a little bit more simply, this just means that cold temperatures make solids extremely weak and extremely brittle, so they break super easily. Let's go ahead and take a look at what happens when we submerge a flour in liquid nitrogen, and then we'll just drop it on a table.
If I were to submerge the flour in liquid nitrogen and I were to smash it against the table, the sound that it makes, is it going to sound like this? Or is it going to sound like glass? Like glass? Anyone else have another guess? Yeah? Glass? Wait, what? Like the plastic? Okay. Do you have a guess? Okay. So let's try it out. So, it's on the floor now, but it broke like glass.
Why did that happen? The cold temperature of liquid nitrogen brought down the flour's structural integrity. Alrighty, that was all about the cold portion of space. Now let's talk about the hot. When a rocket, like the space shuttle, is re-entering Earth's atmosphere, it can get up to 2,910 degrees Fahrenheit. That's pretty hot. To put that in perspective, it takes only 212 degrees Fahrenheit to boil water. When the space shuttle re-enters the atmosphere after being in space, it does not come in nose first. If it came in nose first, the nose cone would actually burst into flames because of the super high speed. Instead, it comes in at a different angle, with the underbelly of the shuttle closest to land. But wouldn't the belly also burst into flames? Isn't it also going super fast? What's stopping it from catching on fire? Well, you're right. The heat is a huge problem. So scientists needed to develop a material that can distribute the heat so that one part doesn't heat up a lot like the nose cone would. And they did it! The material that they developed allows the heat to spread out around the space shuttle, kind of like in the picture on the right, which prevents any one part from catching on fire and getting destroyed. This is important because we want to keep our astronauts alive. Let's do a little demo to see how a chunk of this tile, the black thing in the video, reacts to heat.
I need you to point this laser gun, not at Brandon, but at the black thing right there. Right in the middle. And what temperature do you read? Okay, that's about room temperature, right? Okay, so now we're gonna actually put some heat on this. Hey guys, we're just about to start it up. Okay, so now we're gonna apply a lot of heat to it. So, now try that. What temperature do you read?
Like 200.
Yes! That's the cool part, because Brandon's still able to hold it. That's what I meant.
The space shuttle tile can take a lot of heat, right? That's really nice, especially since when the shuttle re-enters the atmosphere, it gets super hot. The tile protects the astronauts inside from getting cooked. One fun side note, that specific black chunk of tile in the video actually did go into space on one of the missions. Modeling all that is very important for space applications, so we really hoped you learned a lot today. Thanks for watching!